Lab for Oscillations. To introduce this lab, the purpose of this lab is to analyze the change in motion, energy, force, position, and velocity of a hanging mass that is swinging back and forth while oscillating. We can then relate our observations back to fundamental physics principles and model with code and glow script. The system for this experiment is the ball mass and string hanging. The surroundings nothing, and the initial conditions will be addressed during the coded segment of this lab report. The following formulas are needed in fundamental physics principles, including the momentum principle and Newton's second law, but also we use energy for kinetic, the potential energy due to gravitational force, and the potential energy due to the spring force. Total energy is adding all those up together. In terms of the spring, we're finding the net change in length of the spring, which is S, which is the magnitude of L minus L naught. For kinematics, we use position and velocity update formulas, and for force, we use the net force, and then the force of the spring and force due to gravity. In this experiment, in addition to the fundamental physics principles of Newton's second law and the momentum principle, for the lab setup, we have the mass of the ball mass in the video is 0.402 kilograms. Gravity is 9.8 meters per second squared. Here we have the ball mass hanging from this rope, which is 0.7 meters due to the calibration stick in the video. The rope is swinging back and forth, and the ball mass is oscillating at the bottom. T is the period of oscillation, and it's equal to 2 pi times the square root of m over k, which is the constant, and you can get these two formulas from that. Here is the time between frames, which is possibly needed, but it's just good to note. And here is the period with respect to y, which is going to be the vertical change in the oscillation. And this one. Result preview of this experiment. Disclaimer, these graphs are not completely accurate and will be addressed later in this lab, but here we see the kinetic energy, potential energy due to gravity, potential energy due to the spring, and the total energy, which all of these kinetic and potential should add up to the orange delta E. Here we have this kind of oscillation and then the model, but we'll address that later. For the video analysis in Tracker, I did the point mass and tracked the point mass during its oscillation. Here you can see it swinging back and forth, and then here's the oscillation. You get these two graphs and X and Y data in reference to T time. From that, we need to solve for K, L naught, and and S, because L is given, and that's how you do that. In terms of the code, in glow script, we plug in the mass of the ball, 0.402, and here are the initial conditions. I started so here you can kind of see that there's this flat line right here, but I started all of my data down here because here I just started the video a little bit early. Here we have the initial conditions, and then delta T, and then here we have gravity, constant, which we solve for, L naught, which we solve for. L is just going to be the ball position minus the spring position. It's not just the length of L, which is 0.7 meters, and then we have L hat, which is the unit vector, S, which we solve for, and then these are just formulas that we went over in the beginning. Here we have a similar thing, gravity is mg. So this is a formula. This is also a formula for force of spring and F net, which is just going to be combining the force of the spring and force due to gravity. Gravity is negative because it's downward pointing. We have to remember that. These are the two velocity and position update formulas. And then it's same kind of thing down here. Again, when you're doing delta K, you do final minus initial. Here is the data that I inputted into GlowScript, and this is just part of it, but these are my data that I got from the tracker. Predicted versus observed motion. In the model, the kinetic and potential energy doesn't equal the total energy, and the kinetic and potential oscillation should mirror each other. We're going to see that in a little bit. And predicted, we do see this is what it's going to look like, and we see those based on the formulas. Discussion. Although I did the guided steps in the analysis process with Tracker and with code and GlowScript, something is causing the model to be not displayed correctly. As a result, I wanted to show and explain what the coded model should produce. Here we have the spring potential. The red is the gravitational potential energy, the blue is the kinetic energy, and the black is the total energy. So as you see, if you add all of these up, including their signs, it should equal the total energy. And they're oscillating back and forth, going from kinetic to potential energy at the extremes, and then in the middle, it's a little mix of both. As a result, the energy principle would not be satisfied because the kinetic energy line at any point added to the potential energy line at any point doesn't equal the total energy line at that point. If my code model was correct, the kinetic and potential energies would be oscillating, and the total kinetic energy plus the total potential energy at any given point would equal the total energy line. So here, we calculated both the period in terms of x and the period in terms of y, which just is basically the difference is it's referencing horizontal motion versus vertical motion. Thank you so much and have a great day.